So I'm giving a talk on diagrammatic algebra, which is sort of a visual approach inspired by category theory to talk about various compositional structures, such that the visualizations accord with the algebraic laws. So let's get started. So let's say I have a generic function from A to B. Usually people draw this as a dot for the two types, the domain and codomain type, and an arrow for the function type. But let's try dualizing. And by dualizing, I mean, right now, the objects or types are zero-dimensional, they're points, and the functions and maps are one-dimensional, they're arrows. Let's swap those where now the types are going to be one-dimensional strings or wires, and the functions are going to be dots, zero-dimensional dots. But let's allow for internal structure. Part of the goal of this isn't just to write things this way because it's cute, but it's also to place into relief how we create big functions by composing small functions in intricate ways. So let's replace the dot with a box, which implies that that box could have some kind of inner organs that correspond to other function compositions. So one classic thing we want to talk about is function composition. So I know that semicolon's reserved in Haskell, but in the category theory community, we like to write the flipped version of dot or compose as a semicolon. So that's why this is pseudo Haskell. The reason is that if you read this, if you read the directed graph way of depicting function composition, your eye definitely reads F then G first, unless maybe you grew up in a language where you're reading from right to left. So just to keep things very neat and to keep the types aligned, I prefer the style that many category theories do too. So usually we render things like this. We squish the F and G into one function, the intermediate type B goes away, and for the sake of reading aloud, this semicolon symbol, let's read it as then. So maybe before you said G of F, now you could say F then G. Okay. So in strings, composition is just as easy, maybe even easier. It's just literally two boxes, two beads along a string, like a necklace. And composition is you're just squishing the boxes together into a single box. Then we can abstract this, if you want, into the act of composition itself, which is a higher order function, as you know. And we'll depict it with a picture like this, which we call a wiring diagram or a schematic. So it's like a fractal or a holon, if you have read Arthur Kessler. And I like to call the internal things slots, and the external output, the outer box, a screen. So it's almost like imagine you're plugging in cartridges that then render an image onto a screen. So if I want to do F then G, I literally will plug in an F into the first box and a G into the second box. So what advantage do we get? Well, first of all, there's an immediate generalization to n-ary composition, and I call this n-chain. And there's also interesting special cases that maybe we before viewed as different things, but now we can view them as part of the same pattern. So when n equals 1, you're composing a single function. What does that mean? You're literally just returning that function itself. So all it is a higher order identity. But what about 0 inputs? Well, that has a meaning too. 0 inputs means that there's literally, that the input type is nothing, it's the unit tuple. And the output type is the tuple from the mapping type from A to itself, or A0 to A0, if you like, to continue those patterns. So, whereas the previous one, which I called a NERD, was a higher order identity, this is a function that picks out the lower order identity. So it sends that unique term of the type unit to the identity function between A and A. So now, function composition, identity maps, and higher order identity maps are all part of just one sequence of composition operators. So that's nice for conceptual parsimony. But we classically talked about things like, associativity, unitality. So here's how this picture can present those concepts. So the goal is this. You can nest wiring diagrams into wiring diagrams. And by that I mean the smaller slots, you could put into those slots a wiring diagram itself, so you have nested ones. And the only rule you need, the only coherence rule, instead of saying associativity, unitality, you only just say intermediary boxes don't matter. When you plug in a smaller wiring diagram into a bigger wiring diagram, you can just erase all the intermediary boxes. So both the things on the left and right, which correspond to the two different ways of composing three things, if you erase the intermediate box, it just says, oh, we just have 3 chain. That's it. And unitality works a similar way. You put in the 0-ary box into one of the slots, and the unary box into the other slot, erase the intermediary boxes, and you have exactly the middle box, which is inert, which says do nothing. And that precisely codifies unitality, which says that if you have F followed by identity, that equals F. And if you have identity followed by F, you have F. And note, I should have been more explicit about this, we're going to draw the identity box, the box that doesn't do anything, as literally just a string. We're making very clear that it doesn't do anything by not even giving it a box notation, so no changes occurring with it. So as you notice, this algebraic property of F then ID equals F, and ID then F equals F, is just codified here as literally children's geometry. You can slide boxes along the string. So what if we want more intricate compositions? Well, we can introduce multivariate maps. So I'm going to give the notation of the tuple type A comma B as 2 parallel wires, or parallel strings. So then a multivariate map will be a box with multiple input wires and multiple output wires. So I call the places where the wires hook up into the back and the front ports. In the front, I'll call them imports. In the back, I'll call them exports. Or rather, in the beginning of it, the left side, I'll call them imports. On the right side, the output, I'll call them exports. So we're going to write functions like this in uncurried form, just for consistency of some kind. You don't have to if you don't want to. So this would be a map from tuple AB to tuple CD. So now we have more complicated compositions and wiring diagrams you can have. All of a sudden, we could move around the various inputs and outputs of the smaller boxes and plug them into any of the other smaller boxes we want. So I call these things flows. So what chains are to univariate maps, flows are to multivariate maps. So here's the type of this flow. You have as input slot 1, which is the top left one, and let's say that's a map from A to the tuple M comma J, where I'm using the convention that M is the higher output and J is the lower output in terms of height. Then slot 2, the lowest box in the center, has as input J comma B. Notice that J coming from the previous slot, and B is one of the wires that are coming into the larger box from the beginning. And then so on and so forth. And the screen, the total thing, is a map from A and B, the very beginning ports, to Y and Z, the outer ports. So how would you implement this in Haskell? It's not too bad. So I'm a big pretty printer, if you can tell. So flow of FGH is the map. So I'm putting this in a lambda form because I want to emphasize that AB and YZ are the outermost inputs and outputs. And in the middle is sort of the, I guess, control flow that you have to do to see what gets plugged into what. So let MJ equals F of A, that's the output of the first slot. Let PZ equals G of JB, output of the second slot, and so on. So it's not too complicated, and this can get generalized to far more intricate wiring diagrams. So one thing we want to worry about is this thing called strictification or weakness. So technically, the tuple A comma B comma C is not the same thing as the tuple A comma B comma C. In our diagrams, we're really going to look at these as equal. There's a category theoretic reason why we're allowed to do this, and it's safe, and it's called strictification. I'm going to elide that notion, but feel free to Google it. And then similarly, we have unitality, where if you have the unit type as part of your tuple, you can just collapse that into the original type in either slot. And what we're going to do is we're going to draw the unit type as an invisible string, in the sense that because the unit type is the identity or the unit in terms of tupling, we want 2 parallel arrows where one of them is the unit type to look like one parallel arrow. So an example of how this would end up looking like in practice is, let's say you just had a type of something from the unit type to A, from any type A, and it just picked out an element of A. You would draw it like this with no input wire. So we also have swap maps. A to B goes to B to A. And we're going to draw it with literally a crossing. And this is going to satisfy a bunch of properties that I'm not going to get too detailed into, but you can probably see how these would be implemented in Haskell. But the whole point is that this is very diagrammatic. The first one says that you can slide beads across the crossing. The second one says that if you treat two strings as though they're a bundle of one string and cross them with the other, that's the same thing as if you did them one by one. And this last one says that if you just swap twice, you'll go back to where you started. But in addition to swap, there's also parallel composition. Sorry, in addition to classical composition, there's also parallel composition, or tensoring if you like. And so if you have a map from A to A prime and a map from B to B prime, you can get a map from AB to A prime B prime. And it's just element-wise. And interestingly, this satisfies the so-called interchange law. If you have 4 boxes arranged in a 2x2 grid, and you first compose them by rows, and then compose them by columns, or if you first compose by columns and then compose by rows, it's the exact same thing. So we really can, just like in the previous world, erase intermediary boxes and just look at this as a single wiring diagram that just has a 2x2 collection of slots. So one interesting thing that we have in addition to these multivariate maps is this sort of what I would call Cartesianness. We have a copy map that says that if we have A, we can always get a map from A to A comma A in the very obvious way. And I'm going to depict that like this with this fork-like thing. And this also has special properties where if I have a map function f, I can slide it through and essentially copy the function itself as well through this copier. And similarly, if I'm copying 2 at once, it's the same thing as if I copy them individually. And dually, just like we can produce extra terms, we can delete terms with this so-called discard. We can always send something to the unit type by just forgetting what we started with. And I'm going to draw that as just a black triangle at the end of the wire. And it's kind of like the end of the road. And the first property says something to the effect of, well, if you applied a function and then you discarded it, it's the same thing as it's the same as though you discarded things right away. And similarly, if you discard a tuple, it's the same thing as if you discarded them separately. This also has an application to projection maps. So, for example, if you want to map from A comma B to A, i.e. first, or A comma B to B, i.e. second, you can draw it in terms of discarding one of the two. So, projection maps then also have a visual modification. So, these laws satisfy so-called co-monoidality. So, it's co-associative, which means that if you first copy it and then you copy the leftward output, or if you first copy it and then you copy the rightward output, if you indeed do the aligning that we did about the strictness of associativity, they are equal. And the same thing goes with unitality. So if you have strictification, you have these diagrams. So here's a proposition called universality of product, which really says that if you have a map with 2 outputs, you could split it up into 2 component maps. And these are the exact same data. And this is part of a world called universality, which category theory deals a lot with, and a ton of nice properties, which unfortunately I won't have the time to really go into, follow from them. But here's the isomorphism. We want to map one way, it's called fork. And usually fork is drawn as this upside down triangle, so I did the most ASCII thing I could with that. So it just says if you have a map from A to, if you have inputs, a map from A to B, and a map from A to C, I can make a map from A to B comma C. And it just says, literally, each component is, you do F on the first component, G on the second component. So we're going to draw it like this, because this really is a composition of copy and parallel composition. So that's why we're drawing it in this manner. This is a copy map, we're first copying. So we're going from A to A comma A, and then we're applying F to the first one, G to the second one. So this is the wiring diagram corresponding to fork. And then similarly, this unfork, it looks slightly more complicated, but that's just due to the notation available to us. and you simply just you take the tuple that corresponds to projecting each respective output component. So how do we prove that these are isomorphisms? Well, we want to show that one composed of the other gives you the higher order identity. Well, the higher order identity, remember, is inert. And this is how you do it. So remember, so here we're going to plug unfork into fork. Sorry, we're going to plug fork into unfork. So remember, fork looks like this, and unfork looks like this. So we have this outside unfork, and inside, these are mini forks inside of it. Well, here we're going to apply the discard property that says that this one and this one don't matter anymore. And then you literally just have co-unitality, where everything but these two bubbles that correspond to the boxes just go away by co-unitality. So you're left with this higher order inert map, because nothing's happening. You plug in a box here, up in a box here, and you erase the intermediate box. You just get the original boxes back. And a similar argument holds for the other way around. So this diagrammatic approach is powerful in that it allows us to really abstract on where the various terms are going and look at a way to render the higher order maps themselves so that the geometry of how we render the higher order maps codifies within it the algebra of how those higher order maps combine. So another interesting thing we're allowed to have is monoids. So what we're going to do with monoids is we're going to thicken the string into a so-called band. So if a type A is a monoid, we're going to draw it as a band. And we have a binary operation, which again, I'm drawing an uncurried form. I'm writing an uncurried form. And we're going to draw it like this. And a unit element, which usually people just view empty as an element of A. I'm viewing it as a map from the empty type to A. From the unit type, sorry. And a monoid will satisfy associativity. And why did we thicken these bands? Because literally, looking at these as Plato, two-dimensional Plato at least, gives you the fact that this left one equals this right one. All you're doing is doing some kind of sliding with the clay. And same thing goes with unitality. And these properties allow you to have, for any given number of arguments, a single map, which is what in Haskell is m concat. And this is just an example with 6, but literally for any number of arguments, there's exactly one map that collapses them into that operation. And that is able to be the case. The uniqueness is justified by these associativity and unitality axioms. So what about comonoids? So comonoids may seem mysterious, but in principle, it should literally be monoids backwards. So instead of something that goes from 2 to 1, something goes from 1 to 2. Instead of something that goes from 0 to 1, something goes from 1 to 0. But because of this Cartesianness, in Hask, or in the math world set, almost the same thing conceptually, any comonoid, A delta epsilon, literally reduces to A copy discard. Why is that? Well, terminality, which means that to the unit type, there's just only one unique map always, means that epsilon has to be discarded. There's literally no other map we can have. But universality means that delta has to equal the fork of two component maps. So we have something that looks like this. We have the fork of delta 0 and delta 1, and that has to equal by co-unitality, the identity. And that has to equal the fork of delta 0, delta 1, discarding the other one. Well, applying the discard map, this reduces to the fact that delta 0 equals identity equals delta 1. So delta has to equal the fork of identity and identity, which literally is the copy map. So the lesson here is, if you want non-trivial comonoids, you have to work in a non-Cartesian category. You can't work in classical Hask. Now, if you've encountered linear types, in linear type systems this is no longer true. You don't have copy and discard, and hence, in principle, you can have non-trivial comonoids. So, I'm going to end with a more general picture. So, what David Spivak and I have been starting to call organizational theory, or the theory of organizations, is it's an unbiased and flexible approach to compositionality. And what do I mean by unbiased? Well, in the case of this m concat, you could just have m concat instead of mappend and mempty. And it's a strictly general version. and reduces to them in the case of 2 or 0 arguments. Similarly, we want to do this at the higher level instead of with monoids, literally with monoidal categories or any kind of structure we want. Cartesian monoidal, symmetric monoidal. Do you want to have braids? Do you want to have duals? Whatever it is that you want to encode, you encode it in terms of the collection of wiring diagrams or schematics that you're allowed to have, i.e. the collection of valid compositions. And you have a collection of labels for the wires, and those are literally your types. And a collection of boxes, which are literally the maps you're allowed to make. And as long as you can define what it means to nest wiring diagrams, and you prove that nesting is coherent, i.e. if you nest 3 in a row, that's the same thing if you consider the first 2 nestings collapsed and then the latter one, or the last 2 nestings collapsed and then the former one. So that's sort of the general approach to compositionality, and I'm interested in trying to implement something like this in Haskell or maybe independently typed an analog like Idris. So if anyone's interested in talking to me about that, that'd be really cool. So thanks a lot for listening to me. If you have any questions about category theory or want to discuss this stuff.
What kind of scenario is this useful?
In what is this useful?
What kind of scenario is this useful?
Well, let's say you have a factory or whatever, and each and every single machine corresponds to some kind of, state machine, and you want to compose them. And the way they are interfacing with each other is via intricate wiring, where one has like 3 outputs, it's feeding its state into this one, it's feeding its state into that one, etc. And what if you want to abstract the compositional structure of those from what the individual pieces are allowed to be and behave by? This allows you to do it. So one paper that David Spivak and I co-authored does this for dynamical systems in the continuous differential equation sense, where each of these boxes corresponds to a differential equation of some kind. And we, from there, give you a rule for how to produce the external differential equation of the hybrid system that corresponds to all 3 of these pieces. So if you have really a Russian doll of systems or functions, or really any kind of structure where there's a good way to compose it or not, this gives you a domain general way to talk about those compositions that are as agnostic as possible about the constituents. So that's kind of an answer.
So do you see these as like an alternative to normal community diagrams?
Yeah, it really is essentially an alternative. I would say it's weaker than an alternative. It's more just a way to draw commutative diagrams differently. So, for example, one that's very visible. So let's look at this one. We could draw this as a commutative diagram where there's on top an arrow, that's F, and on the bottom, copy. And on the leftward, I know it's hard to visualize, on the leftward, going downwards, you have copy and then F times F. And the fact that those commute correspond to this. But this is sort of a lot easier to talk about because I feel like it really shows you the way that the pieces interact more than the commutative diagrams, because the commutative diagrams, I feel, still privilege the objects and not the arrows, and this is functional programming, so we want to privilege the arrows. And the arrows are where the intricate algebraic structure lies more than in the object. So this kind of allows us to place those into relief. So I would say it's just a different language for commutative diagrams, and one that, if you do have a diagrammatic way to render a given map, which, by the way, you don't always have that ability, I think it's more instructive, both pedagogically and even at the research level when you're doing stuff. It's just easier to follow with your eyes and, narrate in your head what the conceptual story is.
So you were talking about the comonoid, and I kind of think I get why you can't have that in Haskell or maybe whatever family of categories Haskell lives in. But what would be a what would be a handy comonoid to have? What's like some intuition there?
That might be something that so far mathematicians might care about more than programmers, although I think that might change with linear types, but I only know about linear types as opposed to what in practice is really useful to have in them. But in the context of like tensor algebra, where the product is like the tensor product of vector spaces, one often does have comonoids flying around that are important to the algebraic structure of the theory. I highly suspect that there's a way that those map onto in a non-trivial sense to something like linear types, since linear types are just symmetric radal categories. But I don't have a semantics in place in my head for what they correspond to. But note that there really are mathematicians who care about these comonoids. And also, there's a lot of interesting things that happen when you have both a monoid and a comonoid on the same type, and then the monoid and comonoid interact in interesting ways. And a lot of the time you get interesting topology coming from that. So it turns out that actually, if you have this thing called a Frobenius monoid, where, well, let's call it a commutative Frobenius monoid. You have a commutative monoid, a co-commutative comonoid, and they interact in a certain way. You can replicate the entire theory of two-dimensional manifolds in a purely algebraic sense. And this gives a really deep duality between category theory and algebra, and this world of pure symbols, and the world of literally manifolds and movies of manifolds that we see in like geometry and physics. So that's something that a lot of people think is key to investigating the eventual connection at a fundamental level between quantum theory and general relativity. Because they think monoidal non-Cartesian categories are the structure that encodes those interactions most faithfully, but I'm not an expert on those topics.
So you said you want to do something in Haskell regarding this, so what the work you want to do in Haskell entails? Like you want to build like a DSL to generate this kind of stuff, or?
Yeah, exactly. Like ideally, I'd have a DSL that the user inputs this in the most intuitive, friendly way possible, like what their interconnectedness is, and I generate this code. And it seems pretty systematic to do that. So that could be nice, and in a lot of these applied category theory papers that I think need implementing, like Solomon and I are interested in implementing some of the stuff going on with machine learning at a wiring diagram way, you really need, or I don't want to say need, it would be very helpful to have just a DSL that could just spit these out right away.
You know, there's a kind of joke package for Haskell called Needle.
I didn't know that.
It's a template Haskell, you know, whatever. It lets you wire diagrams in ASCII, like really? That, and it will generate the code. It's the equivalent to something written in arrow notation, which is basically that. I have no idea. I mean, it's so absurd that
and
it works.
Is it a joke, actually a joke, or really?
No, I mean, it was posted as a blog post like 2-3 years ago, and so there you can. It's on Hackage.
Wow.
But it's like has like 5 commits to it. Even though I think it is like really interesting, and even to just parse these things in ASCII is kind of like non-trivial. But then also to be able to like generate the code, and I took it and turn it into like more, like you can build functions that are interesting using it, but anyway, I can point you to it.
That's super cool.
Although I don't think that's the most intuitive way of inputting code, it definitely like demonstrates that it's possible.
It'd be amazing if somebody could literally do a drag and drop like thing with these wires, where you just like, click on a port, drag the line to another port or whatever, it generates.
Can you talk a little bit about the similarities and differences between diagrammatics and arrows in Haskell?
In the arrows library, I've only read like the basic intro page, so I don't think I can say anything too intelligent. But I know that when I saw arrows, it did not have the full suite of these flows that you want. Well, either A, they don't, or B, I wasn't clever enough to discern that they did.
Have you seen the talk from Konal about compiling to categories or something?
I haven't seen it. I've seen his other talk which references it on automatic differentiation, but I'm very interested. What he does is in a very similar vein.
I think so. Is I understand you wanna build something where you can like build this diagram in a visual way and get the code, versus what
He does the opposite.
he's doing is he's using like this type classes up to like Cartesian close category, all the type classes after that and then he's like basically generating the diagram. So basically need something in reverse, right?
Yeah, definitely. That's exactly it. Thanks again. I really enjoyed speaking.